At this point, we're ready to start solving differential equations that are non-homogeneous. We're focusing on constant coefficient linear equations, and now we're going to look at what happens when we have a forcing term. First thing I'm going to do is just come up with an example of how a differential equation might be derived that is non-homogeneous, and then we'll go over and talk about what steps you need to do, and then start doing some examples. So this is going to be non-homogeneous, and this is particular to constant coefficient. If we don't have constant coefficient functions, this is going to break down, and they need to be linear. So whenever you're faced with solving a differential equation, the very first thing you should do is identify what kind it is, and that's going to help guide you to figure out what you need to do. So let's look at an example where this comes up. Suppose we have a mass on a spring, and it's on a horizontal table. And the question is what if we apply a constant 1 Newton force to the mass? So the idea is we've got our table, we've got our mass, it's attached to a spring, and we're going to pull it to the right with a constant 1 Newton meter force. So we're going to set x equals 0, again, is going to be the equilibrium point. So if there's no force or anything acting on it, that's where everything is balanced and there's no change in the system. At any given time, we're going to call the position x of t. So the displacement is going to be x of t minus 0, or just x of t. And that's going to be important in terms of finding the spring force. So for our free body diagram, we have our mass, we have a force of 1 Newton. And I forgot to add, there's another force going to do to friction. And we're going to assume that that's proportional to the velocity. So that means we have a force of friction that's going to be equal to minus b times the velocity. And for the spring, we're going to assume a linear spring satisfying Hooke's law. So the force is going to be minus k x of t. So now applying Newton's second law, the derivative of the momentum, it's going to be the sum of the forces. So I have minus kx minus b vx, and then a plus 1 due to that 1 Newton force. So for the mass is constant, I can pull that out from the derivative. And the velocity then is going to be the derivative of the position. I'm just going to add the 1. And the derivative of the velocity is the acceleration, and that's the second derivative of the position. And if I add these to both sides, I end up with a constant coefficient second order differential equation. It's linear. What makes this different from what we had before is we have something that's not 0 on the right hand side. It's going to make it non-homogeneous. So the question is what do we do? And we are going to guess a solution. And if we make a bad guess, it's going to be really important for us to recognize it and then go back and make a new guess. And so the idea is, by the way, we can't just call it guessing because this is the math department. We call this the method of undetermined coefficients. And the reason we do this is we're going to just make a general form. We're going to ask what kind of function do we have, and what kind of function, when we take derivatives and add them together, is going to give us that. So the first thing we asked is what kind of function do we have on the right, or what kind of forcing function? And then we have to ask what kind of function gives us this after we take derivatives. And it's important to keep in mind that this method, when it works, is usually the easiest thing, and the easiest in the sense it's most straightforward. But when it doesn't work, it's there's basically nothing you can do but move on and do something else. So this is only going to work for functions where we can do this second thing, where we can make this guess. If you cannot do that, then you just go do something else. It's not a big deal. And again, it's going to be really important to recognize if things aren't working out, to stop and go back and do something different. All right. So the idea is we have higher order linear constant coefficient equation, and it's not equal to 0. It's equal to something that's a function of time that's not 0. In our previous example, we had g of t equals 1. The first step is you're going to solve the homogeneous equation. And for reasons we're going to see later, it's absolutely vital that you do this first, because there are times when the guess we make for g is going to be the same as the homogeneous equation. And if that's the case, we have to be able to react and recognize what's going to happen if we make that guess. So for the homogeneous equation, we're looking at a different equation. So we say the solution is x sub h for homogeneous. And instead of g, we make it 0. Okay. Second step is, this is going to look a little weird. We're going to solve for the particular equation, but we basically just completely ignore the homogeneous equation in this second step. So we kind of divide and conquer. So without any thought to the homogeneous solution, we now solve this thing. Once we do this, we got to be very careful. We have to compare xp and xh. And if we see that our guess for xp happens to overlap with our guess for xh, you multiply by t. Okay, and this is the guess for our xp. And then once we do this, then we plug our guess for xp into the original equation, and we solve for any unknown constants to solve the equation. So our guess for xp is going to be a very general thing with lots of unknown parameters, and we're going to plug it into the equation and ask what it implies and figure out if we can figure out what those parameters are. After we've done that, we're going to form a general solution. That's an A. We're going to form a general solution, and that's going to be the sum of the homogeneous and the particular. If we're just asked to get a general solution, then we stop. If we need the solution, then we're going to use initial conditions to solve for any remaining constants. And those remaining constants are going to come from the homogeneous equation. All right. So question then is, why do we have to do this step? And why is that something we need to be careful of? And the reason we need to be careful of this is that we play games. Suppose we have a solution to the homogeneous equation, and we have a solution to the particular equation, or particular solution to the original equation. The claim is the sum is a solution. And the reason for that is if we take this thing and plug it into the original equation, what happens? We have a times the second derivative of x, and x is x homogeneous solution plus particular solution. B times the first derivative of the homogeneous plus particular solution, and plus C times the homogeneous plus the particular solution. This is linear, so this becomes A. This becomes the second derivative of the homogeneous plus the second derivative of the particular solution. This now becomes the first derivative of the homogeneous plus the first derivative of the particular solution, and I'm going to leave this alone. Now, for each of these terms, I'm going to multiply through by the A, multiply through by the B, and then by the C. So that becomes that term, and then for the first derivative term, I multiply through by the B, and then finally for the zero order term, I multiply through by the C. Now I'm going to collect anything with an XH, or the homogeneous solutions, and I bring those together. So that becomes this term, and this term. And now I'm going to collect anything with the particular solution. So that becomes A xp double prime plus B xp prime plus C xp. The thing to note is we're assuming the homogeneous solution satisfies that, so that is equal to 0. We're also assuming the particular solution satisfies this, which is the original equation, so that's just g of t. So I get 0 plus g of t is just g of t. Okay, so because of that going to 0, I need to include my homogeneous into the original equation. All right. So let's, at this point, we're just going to do some examples and see how this plays out, because it's a little weird. All right, so for example, suppose you have x double prime plus 4x prime plus 4x equals 1. It's constant coefficient, it's linear, but it's non-homogeneous. The very first thing I do is focus on the homogeneous solution. The homogeneous solution is the exact same thing, only anything without an x I set equal to 0. So I assume that it's an exponential function, and I'm going to plug it back into that equation. So I'm going to take two derivatives. The first derivative is just the original function times n. Second derivative is the original function times n squared. Plug it into this homogeneous equation. So the second derivative is the exponential times n squared, plus 4 times the first derivative is the exponential times n, plus 4 times the homogeneous, which is 4 times the exponential function. Set that equal to 0. I notice I can factor that out. And this is my original homogeneous equation. I don't want that to be 0. So I can divide that through, and I'm left with n squared plus 4n plus 4, which means that n squared plus 4n plus 4 is 0. I can see how to factor that, so I'm not going to use the quadratic equation. So I get a double root with n equals -2. So that means my homogeneous solution is going to be R1 e to the minus 2t. And then I'm going to have, because it's a double root, I'm going to take this and multiply by 2. So there's my homogeneous equation. Now for my particular equation. I'm going to make a guess. And coming back to this equation, I'm looking at this 1. So it's a polynomial. And I know that if I take a derivative of a polynomial, I'm going to get another polynomial. So I'm going to guess a polynomial. And because this is a polynomial of degree 0, I know that when I take derivatives, it's going to be a polynomial of lower degree. So my guess is going to be a polynomial of the same degree. So it's going to be a polynomial is the first thing. And the second thing is it's going to be a polynomial of degree 0. So I'm going to write out the most general polynomial of degree 0 I can imagine, plug it back into the equation and ask what does that imply. And so the most general thing I can imagine is just a polynomial of degree 0, which is just c0 times x to the 0. And x to the 0 is 1. And that c0 is going to be a constant. So I'm just going to imagine that xp is equal to c0, where c0 is a constant. I'm going to plug it back into my original equation and ask if that helps me figure out what c0 is. So I'm going to need a derivative. Derivative of a constant is 0. Second derivative is the derivative of 0, which is 0. So I'm going to take this, this, and this and plug it into here. So x double prime is 0, plus 4 times x prime is 0, plus 4 times x is c0. And if it's a solution, that has to equal 1. So I get 0, 0, plus 4, 0 is 1. And now notice I have, and this is extremely important, that when at this point you stop and ask, is the left-hand side consistent with the right-hand side? I have a constant on the left-hand side and a constant on the right-hand side. The only way that this can be true is if the constant is equal to the constant. So if I solve for c0, I get c0 is 1/4. Okay. So that means then I started off with x double prime plus 4x prime plus 4x is 1. I found a homogeneous solution was R1 e to the minus 2t plus R2 e, it was a double root, R2t e to the minus 2t. My particular solution was C0, which was 1/4. So my final solution then is x equals the homogeneous, which is R1 e to the minus 2t plus R2t e to the minus 2t plus the particular, which gives me that. And now I'm going to do a quick check to see if this works. So if I take a derivative of this exponential is going to be minus 2 times R1 e to the minus 2t. Derivative of this, I'm going to use the product rule. Derivative of t is 1. So I get R2 e to the minus 2t. And then derivative of the second term, so I'm going to have R2t is exponential times the derivative of the minus 2. And the derivative of 1/4 is 0. Now I take a second derivative. So this is going to be minus 2 squared, R1 e to the minus 2, because that's the derivative of the exponential. I already have a minus 2. Here, this is derivative of exponential, so it's going to be the exponential times the derivative of minus 2t, which is minus 2. And then here I have to use the product rule. So I have minus 2 R2, and I've got to be careful. So I'm focused now on t times e to the minus 2t. So derivative of t is 1, so I get e to the minus 2t, then plus t, then the derivative of e to the minus 2t is e to the minus 2t times minus 2. And let me clean that up before I plug it back in. So I get 4 R1 e to the minus 2t from this term, minus 2 r2 e to the minus 2t. And now if I distribute this minus 2 r2, I get minus 2 r2 e to the minus 2t. Minus 2 times minus 2 is 4. Then I'm going to have r2 t e to the minus 2t. Is that right? Minus 2 r2 t e to the minus 2 times minus 2 is 4. Okay. And again, I'm checking to see if this is right. All right. So I'm going to plug this back into the original equations. So let me clean this up one last time because this is still a bit of a mess. Leave that alone. Minus 2 of these is minus 4 of those terms. And I'm going to leave this term alone. So it's plus 4 r2t to the minus 2t. Okay. So x double prime is 4r1 e to the minus 2t minus 4 r2 e to the minus 2t plus 4 r2 t e to the minus 2t plus 4 times x prime. So that's going to be this monster. It's minus 2 r1 e to the minus 2t plus r2 e to the minus 2t plus r2 t e to the minus 2t times minus 2 plus 4x. So it's going to be plus 4 times this. So I get r1 e to the minus 2t plus r2 t e to the minus 2t plus 1/4. And I'm going to clean this up, and I'm going to hope that in the end I get 1. If I don't, I've messed up and I have to go back and redo everything. Let me be careful here. So that was the start of my next line. So I'm going to multiply these 4s through. So I'm going to leave this first row alone. So I just rewrote that. Now when I multiply this 4 through, I'm going to get a minus 8 r1 e to the minus 2t. That takes care of that term. Plus 4 r2 e to the minus 2t. 2t is this term, and then the third term, if I multiply that by 4, I'm going to have 4 times minus 2 is minus 8 r2t e to the minus 2t. Now for the third line, if I'm going to multiply through by the 4, so I get plus 4 r1 e to the minus 2t plus 4 r2 e to the minus 2t. Something's wrong. Yep. I screwed up. This is a t there. Okay. Plus, sorry about that. I'm going to be very careful here. That t goes from right there. Okay. And then plus 4 times 1/4. Notice now, 4 minus 8 plus 4 of these terms adds up to 0. Minus 4 plus 4 of those terms adds up to 0. 4 minus 8 plus 4 of those terms equals 0. And I'm just left with 4 times minus 4, which is 1. And that's my g of t. So life is good.